One is the banquet tonight. Reception 6:30, banquet's at 7. It's in this room. And there are no banquet tickets for those of you wondering. As long as you've registered, you're welcome to come to the dinner. Another item that's coming up, the next Canadian Symposium on Catalysis will be held in Kingston 2 years from today. And there are some notices. These are at the registration desk at the front there. If you like, pick one up and put it on your calendar for 2 years from today. Okay, I think we're ready to go. So my privilege to entertain or to introduce the next plenary speaker, Professor Roel Prins. He's a professor of catalysis at the Federal School of Technology in Zurich. A little bit about his career. His PhD in 1967 from the University of Amsterdam. He spent 10 years with Shell, both at the US and in the Netherlands. The next 10 years at the University of Technology in Eindhoven. And since that time, 1987, he's been at the Federal School of Technology in Zurich. He remains a corresponding member of the Royal Dutch Academy of Science, and is on the advisory committee of the Swiss Light Source. And he's also, most of you know, editor of Journal of Catalysis. Professor Prins. His talk is shortened, EXAFS in Catalysis.
Thank you very much, and thank you very much for the invitation to come here. What I will do is I will tell you about applications of EXAFS in catalysis. It is a sort of mixture of tutorial on the one hand and latest results on the other hand. I think not all of you are too familiar with EXAFS, some of you are. So for some of you there will be at the end some new things, and for those of you who are not too familiar with it, there is something especially in the beginning. So, what is EXAFS? EXAFS is nothing but, now I need a pointer. Okay. If you have an atom, and for instance, it has electrons in a deep core level, let's say a 1s level. And if you have sufficient energy, and normally this is then, if it's a 1s level, it is X-rays, you can kick the electron out. And if it's an atom and it has no surrounding atoms, then the electron goes out, and in the classic picture you have a free wave going out, and if you just bring it out of above the Fermi level, then it has some kinetic energy, so it has a long wavelength. If it has a lot of kinetic energy, then it has a short wavelength. And what you will see then in the X-ray absorption is that if the energy is just enough to bring it out, you suddenly have an absorption, and from there on a slowly decreasing absorption coefficient. However, if there are atoms surrounding this atom, then what can happen is that in the first place you still have what I showed you in the picture before, is that the majority of electrons will go out and will not see the neighboring atoms because space is very empty there. So you still have a sort of background as before, but an electron which is going into the direction of a neighboring atom can be scattered by this neighboring atom. It is as if you're making a standing wave between the point where the electron is starting and where the electron is scattered by the backscattering atom. And because of this standing wave now, you suddenly get an increase in the absorption coefficient of the original X-ray photon. And then you see a peak in the spectrum. And you can see several peaks every time you get a so-called resonance effect. You have this. But it's just a small fraction of the total number of electrons going out. So the majority is still in this structureless background. So what we must do is we must take away the structureless background, because that doesn't contain any information. And then we are left with those electrons which just do this resonance, those peaks here. And these peaks are because we are having this scattering effect. And in another type of pictorial view, what happens is, here is your original atom, here you kick out your electron, and now the electron goes out as a spherical wave, and it bounces into the neighboring atoms and is backscattered. So you get an interference effect between the the outgoing wave and the backcoming wave. So in a classic effect, it's like throwing a stone in the pool and you'll see the ripples. And you can have multiple scattering, you can have single scattering to the first shell of neighbors, to the second shell of neighbors, and so on. And because of this interference effect is dependent on the type of atom, especially the backscattering atom, on the distance. So you can get information, if you would analyze those peaks, you would get information on number and kind of neighbors, on the distance, and maybe on the disorder. Because you end up with a formula which I will not go into too much, but it looks like this. First of all, you have a sinus type of an argument, which is because of the outgoing and backgoing wave. So it's an interference effect. So it's either a sine or a cosine or an exponential, whatever way you want to write it. And then there is a damping effect because, and this is like in XPS, because the electron goes out and eventually scattered so many times that it loses its information, there is no information left. Because of this damping effect, you can't see much more than a few shells surrounding the original atom. So in that sense, it is not as good as X-ray diffraction. On the other hand, it is for certain materials better than X-ray diffraction because you don't need long distance coherence. You don't need single crystals because you only need a well-defined surrounding of this atom here. So on a local scale, you must have structure. And if you have that, you can use this technique to determine that structure. So and therefore, for that particular reason, it is so important for catalysis. Because in catalysis, we often have very small catalyst particles, which are too small to be seen in XRD. And then you may still be able to see them in EXAFS and determine the structures surrounding each atom. The other thing is it's element specific, because I can kick out a 1s electron from this atom A, but if this would be an atom B, and if this would be a different atom, its 1s level, it's at another energy. So I can use another X-ray energy to kick an electron out of that. And I can use this now as the light source from which electrons come out and are scattered. So I can see all the atoms one by one, and I can look at all the environments, and then in the end I get a complete picture. So also because of that reason, it's element specific, because the 1s levels or the 2p levels or the whatever have you of the elements are far apart, so it's easy to distinguish them, and you can be very element specific. You can do it under in situ conditions because we are talking about an X-ray technique. So you just have a chamber and you have windows, and you have quite a choice of materials of the windows, and the X-rays go through like they go through your body when you go to the hospital. And that makes the technique very nice for amorphous materials, and specifically here today for catalysis. So here is an EXAFS spectrum. We have now the jump. So suddenly, in this case, we are at 7,000, which is, what is it, cobalt or nickel, and then so suddenly you kick out the 1s electron, you have enough energy, and then the electrons, which will not see the neighbors, is the smooth background, and the ripples, those are the resonances where the electrons are seeing the neighbors. Now, very close to the edge, we give it a different name. It's not called extended X-ray absorption fine structure, extended, because as you see, it can go on over 1,000 electron volts, a lot of energy. But close to the edge, we have the X-ray absorption near edge structure. It has also been given other names, but I will call it Zane. Here, the electron is not going out yet as a free wave. It may go to bound levels. So it's like normal spectroscopy in the UV or whatever have you. It's from a bound to a bound level. And I'll show you later some examples of information that we can get out from this region as well. Here you don't get structural information, you get spectroscopic information, which you can use in an analytic way. Here, in this extended region, you get the structural information. So if we take off that background and we keep the ripples, then here's an EXAFS spectrum. And here's the formula again, and because of all those sinuses, if I have different kind of neighbors, it's summation of sinuses. As You see it's a summation. So you get interference, so you get something which looks like, well, there are many contributions there. How do we analyze that? Well, up to 1974, this was kind of a problem, and not many people knew how to handle it. And then Professor Stern from Seattle came up with the idea, which in those days was very new, but nowadays everybody is doing this anywhere in spectroscopy. Just do a Fourier transformation. When you have a formula like that, you just Fourier transform and you get peaks wherever there is a certain R. So if I Fourier transform this and I go from K space, which is energy space, to R space, distance space, I get peaks roughly at the position where my neighboring shells are. So what I see here is that this information contains one shell of neighbors, another shell of neighbors, a third one, a fourth one, maybe a fifth one. And then the question is, what is it? Now, in my first example, I will tell you about what I had written up in the abstract, but I will do more than desulfide. So in my first example, I will give you an example from hydrotreating, and this is carrying water to the sea to this conference. I don't have to explain how important hydrotreating is in Canada and in Germany in Catalysis. This is just to remind you. And so the questions that one can ask and one can try to answer with EXAFS is, what is, for instance, the structure of the promoter nickel atoms which are in the nickel polysulfide catalyst on aluminum? We can ask ourselves questions like, okay, we know that molybdenum disulfide is there. How is it formed? How is it prepared? And what is the size of those crystallines? Those kind of questions you can answer by EXAFS. And I'll show you. So let us zoom in on the nickel. So let us go to 8,000 electron volt edge and look at the EXAFS spectrum there. And let's take the background off. So here is the EXAFS spectrum then. It's multiplied by k to the power 1. And we do a Fourier transform, and we see that we have one main peak, maybe a shoulder here, and maybe, well, definitely another peak here, and then it's most probably noise. I can also do a k to the power 3 transformation. Now I'm a little bit technical, but this is a trick to multiply the region at high k, which then after Fourier transformation is at high r. So now you see that the spectrum is different, but now definitely I have 1, 2 peaks here, and I have my main peak. And what I now can do, I can use my formula to fit those peaks. And if I do that well with the right model compounds or with the right theoretical fitting models, I can tell you what this peak is. And in this case, it is a sulfur neighbor. And there are 3.6 neighbors there at a distance of 2.19 angstroms. And the next peak is a sulfur peak. And there is 0.7 of them at a distance of 275. And then here is a mistake. This should be a molybdenum. There is a molybdenum neighbor, and there is 0.6 of them at a distance of 3.11. And if you now use that information, you might come up with a model like this. Suppose we assume, which we already knew from the Topsoe work, that the nickel or the cobalt is hanging on the edges of the MOS2. And here I have the MOS2 slab with the sulfur layer, another sulfur layer, here in yellow, the molybdenum is in between. Here I've rotated it 90 degrees, so we are looking onto the sulfur plane. And then it's logic to assume that the nickel is hanging on the edge. And where is it then? Now using the EXAFS, you see there were 3.6 neighbors, which is almost 4. So it looks like it might be sitting on 4. And then there was a second shell, which was 0.7. And so this may be 1 in front of it. And then we saw something like 0.7 of a molybdenum. And that may be the distance from the nickel to that molybdenum. In the ideal structure, there should be 2. So this suggests that there is some disorder. Not all the sites are really seeing the ideal picture which you have here. Or there is a reason that we have lost intensity. I'll come back to that. So this is the kind of thing you can do with EXAFS. You can measure the spectrum, you can analyze it, and you can come up with ideas what the neighboring atoms are. And as I said, this can be done for amorphous substances like this one, which you can hardly see in XRD. It has been done in biochemistry, in the enzymes, in inorganic chemistry, in compounds, clusters, whatever have you. So let me address the second question. how do the MOS2 crystallize form? Now that we do with a technique which is called quick EXAFS. It's just EXAFS, but it's EXAFS on the fly. It's like temperature program reduction. You just increase the temperature, and in this case we just have our cell, which is stainless steel cell, with Mylar windows, or Kapton windows in this case, and we just flow the catalyst, the precursor, the oxidic form, the heptamolybdate, 1 alumina, and we flow it with hydrogen and H2S, 10%, and helium, and we flow through. And of course, when we go to a synchrotron radiation site, in the hutch, in the place, on the beamline, for those of you who are going this afternoon, and for those of us who were already there yesterday, you will see that there are beamlines there, and there are places where you can measure, but this is of course not so easy to just let go the H2S and the hydrogen in that atmosphere here. Like here, you wouldn't be able or allowed to let it go. So you must take your solutions, and we normally take iron salts, because then you get an insoluble iron sulfide, and that is how you trap the H2S. So here you see many spectra, which we do on the fly. So in a couple of seconds, we measure one spectrum, and we add like 4 of them. And that means that one spectrum that you see here is an average of 4, so by the time we go to the next, the temperature has already changed somewhat. But if you do it slow enough that you are not in the danger zone where you see the big changes, then you can do it this way. So here is the temperature in Celsius. So room temperature, fresh catalyst, going up all the way to 400, and from here on we keep the temperature at 400. And what you see is, you see a Fourier transform spectrum. So now you are looking at R space. So you see peaks, and they are around 1, a little bit below and a little bit above. Which immediately says that, okay, yes, it was originally heptamolybdate, so we are looking at a molybdenum EXAFS now. We are looking at 20,000 keV. So we are kicking out 1s electron. And so the molybdenum electron is going out, it looks around, and what does it see? Well, it sees these peaks, and what are they? They must be the oxygen neighbors and the molybdenum neighbors. And we know from the structure they are at short distance. Then we increase, we are still flowing H2S, and you see a new peak come up. And here the shoulder is going. So here is a new peak growing in. I've colored it in with a new color. And then you see that another new peak is coming up here as well. And this peak is disappearing. And in the end, there is another new peak, even more to the right, which is here. And this peak, you cannot see it so well in this presentation, of course, but this peak is also a little bit shifted. And in the end, it looks like a 2-peak spectrum. And that is exactly what you expect for MOS2. So we know at the end we have MOS2, and of course we expect it, but we have definitely 2 intermediate phases. And the question is what? And this is one of the ways to distinguish them. And this is structural information. So if you just take a few of those spectra, you see originally we are in the low region, and then later peaks go in, and we have an intermediate state with a peak here, and then eventually we have a peak like, well, 2.8 or something, and then here. So let's analyze that. We start with heptamolybdate. We all know the structure of heptamolybdate. It is 7 molybdenum, there's a lot of oxygen. The internal oxygens, molybdenum to oxygen, is a long distance. And at the edge, you get the relaxation at the edges. So you get the contraction. So the light blue is a shorter distance. Now the symmetry of the complex is low, so all the dark blue ones, molybdenum dark blue distances, are not all equal. And this is why you saw several peaks. The intermediate situation with a sort of 2 peak, but the 1 peak not totally to the right, it's not 100% sure what you have there. But in analogy to compounds in the literature, like MO2S12 anion or the MO3S13 anion, which were well described and synthesized, and X-ray diffraction was done, you see that that molybdenum sulfur distance is quite low, and also the molybdenum-molybdenum distance is low, because I'll show you that the molybdenum-molybdenum distance in the MOS2 is 3.16. So this is the shorter distance. And the analysis of the spectrum was that in that case you also have two peaks. One was the molybdenum-sulfur, one was the molybdenum-molybdenum. So we think that the intermediate is an amorphous state. Nobody has ever been able to crystallize this intermediate state. And we believe that it is because it is a mixture of everything. You have probably triangles of molybdenum. The infrared suggests that strongly, with disulfur bridge, so S2, two minuses. And you have a sulfur apical in between three, and then you have bridges of sulfur or disulfur bridges. And this is why you can have everything. But in principle, you have the molybdenum-sulfur distance and the molybdenum-molybdenum distance, and the molybdenum-molybdenum distance is on the short side. Because when we go to the final MOS2, we all know that's a slab structure, a Belgian waffle type of system, a sulfur layer, another sulfur layer, and a goodie in between, and only at the edge then can the catalysis be done. That system is then having the molybdenum-molybdenum distance and the molybdenum-sulfur distance. And that brings us to the question, what is the size of those MOS2 crystallites? Can we measure that with EXAFS? And here I'll show you the EXAFS spectrum, Fourier transform, so we see the peaks at certain distances. And in black you have the molybdenite, which is a single crystal. So you see a peak for the molybdenum, and it's molybdenum EXAFS, so at 241 angstroms, you see a sulfur neighbor. At 316 you see a molybdenum neighbor. Then 395 sulfur, and here are peaks, and here is another molybdenum, and here is a molybdenum. This is exactly double the distance of this, because this atom, molybdenum, is right behind this atom. So it's molybdenum, molybdenum, molybdenum in a linear fashion. And this is also called forward scattering, because the electron goes out, goes to the molybdenum neighbor, and continues to go to the second neighbor, forward, and then it's back scattering. So it's called forward scattering. And that's why its intensity is larger than any intensity in between. Now, let's now look at the catalyst. Well, we have done on carbon, we have done on alumina. Here I have an example on carbon, but it doesn't matter. It's a molybdenum disulfide and the one promoted with cobalt, where the nickel looks alike. The first thing to notice is that the first peak goes down in intensity. However, when you do the analysis, the number of neighbors is more or less the same. It's still around 6. It's a little bit lower, meaning that the atoms at the edges don't have the full 6, but they still have quite a few. And so the reason the peak intensity goes down is because of broadening. I'll come back to that. The second peak does go down. And it's also now lower than the first peak. Look at that. And this is an important point in my analysis. Take notice that the second peak is now lower in intensity, peak intensity, than the first peak. Whereas in the single crystal, it's the reverse. All the other peaks are more or less gone, but for this double scattering peak. That is still there. It was quite intense in the single crystal, and you keep something. And this shows immediately that we must be talking about small MOS2 particles. Because in the small MOS2 particle, the molybdenum has sulfur neighbors, and maybe it has a next neighbor, which is that molybdenum, and then it looks like it has no neighbors anymore. So it looks like, from EXAFS, the crystallites must be extremely small. For instance, as small as this. This could explain it. Suppose you had, and now my top part of the Belgian waffle is taken away. So you're looking at the big balls, which are the sulfurs, and the small ones are the molybdenum cations. And you see that, for instance, this molybdenum is having 1, 2, 3, 4 molybdenum neighbors. This one has only 2. So on average, in this case, because EXAFS is a bulk technique, it's an X-ray technique, it looks through my sample. I am looking at every molybdenum atom. So I see this one and I see this one, so my information is averaged. So in this particular picture, the average molybdenum coordination number is 2.8. Here it's 2.7, here it's 3.3, here it's 3.2. So you see, it's low. The analysis of the spectra I showed you of the catalyst gives 4. So maybe the particles are a little bit bigger than this. So it shows you can do, EXAFS in principle can give you information on the size of the crystallites of your catalyst. Unfortunately, in this specific case, there was a big problem. Because electron microscopy had already looked for 10 years at this system. The better electron microscope had been able to see on the real catalyst surface of alumina the MOS2 particles. And they told us that these particles are 30, 40 angstroms, and this is more like 15 to 25 angstroms. So there is a discrepancy by a factor of 2. Now, arrogant as we always are, we always think the others are wrong. And of course it's very easy to come up with a reason why the TEM is wrong, because we are measuring in situ. And electron microscopy in general, 99.9% of the cases are measuring ex situ, that is, they measure in situ, but after having transferred the sample through the air. Now if you do that with any catalyst, it will passivate. So you don't know what will happen to these small particles or to the big particles. So maybe the bigger particles of 40 angstroms are oxidized on the edge, and you don't see that type of a random chaotic molybdenum oxide, and all you see is maybe the molybdenum sulfide in the middle, in the kernel. And therefore, we are right and they are right. So we don't know. However, there is also an internal EXAFS problem. And this is why we weren't happy. And the internal EXAFS problem is this. We all know from surface science that atoms at the edge of a system, they are in a different position than in the middle. And they relax. Because at the outside they have vacuum, at the inside they have a force. And that's different from an atom which has forces from all sides. So normally they relax inward, you get contraction. So here we would have expected that, for instance, take this one here, that the molybdenum distance, all the atoms are at the outside, there is none at the inside. So you would have expected here a molybdenum distance which is shorter than the 3.16 of huge single crystal. And that was not the case. It was perfectly 3.16. So that was already a warning sign. And the other warning sign is that if you look at the forward scattering peak, which is from here to here to here and back, so from this to here and back, in these small particles there aren't too many of those passes. And still we saw the peak, suggesting that the particles were larger than we thought they were. So maybe there is something wrong with the EXAFS analysis. And yes, there is. So the idea came up that maybe the surface science is right, and so maybe at the edges of my crystallite of MOS2 there is a contraction, or there is a different position than in the middle. So when I got a postdoc for a couple of years, I suggested to him, let's try and simulate it by Monte Carlo methods. There are other methods, I'll show you one in a few minutes, but let's first go to this one, because I like this one, because for a chemist it makes sense to start from that side. You start with your chemical intuition, and then you try to come up with answers. Our chemical intuition told us that the inside is different from the outside. So we took 2 rows at the outside to be different. And we allowed it to be different in many ways. We had in general 3 models. In all models, all atoms could be randomly positioned. However, the molybdenum to sulfur distance was always, we kept it the same, 2.41, because the EXAFS showed that that distance never changed, and also that coordination number never changed, and also from an inorganic chemistry point of view, this is the nearest neighbor. So that's the strongest bond. So that's a stiff bond. So there's all reason to believe there is nothing wrong with that, and you don't have to randomize that. However, if you keep the molybdenum to sulfur distance fixed, you can allow the molybdenum distance to vary. So we varied it in a sphere surrounding each molybdenum, and then we randomly put the molybdenum atom there, keeping all the molybdenum sulfur atoms constant. So the computer had to do it, because you can start, for instance, at the edge, and then you can make this well then, but if you're not careful and you put this in the wrong position, not all of them come out within a certain sphere, like only a deviation of 400ths of an angstrom. And so you have to do it by computing. And in a second model, we allowed the edge to contract only half of the positions, for instance this and here. And in a third model, which I'll show you, we allowed this edge to contract and this edge to expand. So here, I'll show you the three models. This is the model where, in principle, there was no contraction at the edge. So in principle, the average value for the metal-metal distance was 3.16. But we allowed it to randomize by 400ths of an angstrom, 800ths of an angstrom, or 1200 of an angstrom. And since we are counting small particles, you of course do not get a smooth curve. But it's, if we would have done thousands of these particles, then automatically, of course, you would have get a nice Gaussian curve. But it's on its way to being a Gaussian curve. Then because of DFT calculation, which assumed there was a short distance of 2.85, we tried that. So you get at the edge now a distortion in addition to the freedom. And the third model, you have a shorter, slightly shorter distance and a slightly larger distance. And what we then did, we then calculated all the average distances, all the distances, we added it up, we averaged it, and then we analyzed it with the classic EXAFS analysis method, which assumed that everything was having the same distance. And here you see the outcome. What you see is that with model 1, just giving the molybdenum atom a random position, but no distortion at the edge yet, you see that it is almost impossible to make this second peak lower than the first peak. I must go to outrageous randomization, Monte Carlo thing, to get it lower. And this is impossible, and I still have too much intensity here. So that model, that I just give every molybdenum atom freedom, doesn't work. I must go to models which have distortion at the edge. When you do that with, at the one edge, a quite strong contraction, you see that, oh sorry, this is the other model. I must go to the next one. Oh, it's here, that's the B model. You see that you do get this second peak then, you can distinguish it. But we never saw it in reality. So this means we have overdone it. We have introduced a shortening which is too strong, otherwise we should have seen it in the experimental spectrum. So this cannot be the truth. So the third model, where we had a contraction as well as an elongation, but they were mild, that works well. You don't see extra peaks in the analysis. You do see now that the second peak goes down, and the analysis now comes up with a coordination number which is 4, which is what we found in the original analysis. But it's only apparent. And it's because of this distortion, and it's because of the randomization of the molybdenum position, that you get this apparent coordination number. And this led us to the following model. The classic analysis method of EXAFS would give you this curve. This is the coordination number that you then can measure and then analyze with the classic theory. And this would be the diameter of an MNOS2 slab. And you see it goes up steeply and then it levels off. And 6 is the maximum, because in the plane of the molybdenum there are only 6 molybdenum neighbors. So if we would see a coordination number of 4 experimentally, this is what we decided originally. Okay, it must be here, so I go down. So my particle is only 10 angstrom in diameter, so I'm looking at very small particles. But I told you, TEM was seeing big ones. Now with this allowing for distortion at the edge, and when we make this now into a new model, we can come up with a new line. And now you see that when my coordination number would be 4, I am here, and now I am close to 35. And then I'm in good agreement with electron microscopy. So the electron microscopy was right. The mistake was in the EXAFS theory. And the mistake in the EXAFS theory was assuming that all distances are equal and are just having a Gaussian distribution. Present, we have done recently some DFT calculations, and indeed this shows a small particle, smaller than the one that is really there. but nevertheless it shows it, because now you can see that especially these molybdenum atoms have now a shorter distance to the other molybdenum. And this distance is from the red one to the blue one, whereas all the other blues in the middle are the 3.16. So you see that indeed the DFT is predicting that you get a shortening, and it can be substantial. So it is to be expected, and indeed if you go for it, and if you do the full analysis, but it's a complicated analysis, and you cannot do such a thing for any system, then you can get it out. Let me give you one example also of an analysis, also of a complication that the classic analysis of EXAFS doesn't give you the right answer, but the full analysis does. And this is a more mathematical way without coming up with chemical explanation. It's the other way around, and this is the theory which was already around. And let me give you an example now from a metal particle, a small platinum particle. Here you have one which is having a dispersion like 40% or so. Just to remind you that a metal particle is not the same as MOS2. We know it. Now the EXAFS theory now is like this. It's the same formula. All I've done, I have replaced this part now by an integral, because I now allow all these distances to be slightly different, and I come up with a probability to have a certain distance from my central atom to my neighboring atom. And all that matters now is the probability function here. If it's Gaussian, it's the classic analysis. If it's a distorted Gaussian, I'm in trouble. And actually that's what I had in this MOS2 particle. I had a distorted Gaussian, because most of my distances were 3.16, but those at the edge were shorter. So I have a skewed distribution. And the way to handle that is to come up with a skewed distribution and put it in here and do then the analysis, and then you get two factors out. And this is the so-called cumulant expansion, or the Taylor expansion. You go to the cumulant, so the 0, the second, the fourth cumulant, and in the phase factor you have the 1, the 3, and the 5. And you can now analyze them. And the classic analysis only has this and this part, and doesn't have the C2, C4, nor the C3 and the C5. And the question is, do we need to add it for a small metal particle? And the answer is yes. For instance, here we have a fit for the E0 correction in the EXAFS without and with. And you see that I have to go to quite high, technically too high, and also varying with temperature, E0 corrections, which is physically nonsense. And when I do include the higher order cumulants, which means I go to a skewed distribution, then everything is all right. I'm talking about a platinum monalumina here, measured in vacuum. My coordination number measured in the classic way would be 5.5. Remember FCC structure of platinum, 12 neighbors in the middle there. So we are below the 50%, so we really have small particles. We see even the oxygen of the alumina on which the bottom platinum is sitting. And also the analysis shows that the analysis without the higher cumulants is giving deviations, whereas when we do it with the cumulants, it's perfect. Also the distance shows there is something wrong when we look at the platinum distance without the higher cumulants. As a function of temperature, the distance goes from 2.74, it dives, which is against physics. When you go up in temperature, you would expect that because of the Debye-Waller factor, you would average over a higher distance, and you have to go up. So this is nonsense. There must be something wrong. So the analysis is wrong because you didn't include the higher order cumulants. If you do that, it's flat. Why this point? Well, by this time, we are at 400 Celsius. We have now removed the hydrogen, because this was a platinum monalumina measured under hydrogen, and now we are at 400, so now the hydrogen is removed, and now we contract. It's known that when the hydrogen is at the surface, you expand a little bit, and when it's in vacuum, you contract. So this is the contraction, and has nothing to do with yes or no cumulants. It's this part which shows the high cumulants must be there, showing that this small metal particle, and it's not unexpected, should be treated in the theory with higher order cumulants, in other words, with a skewed distribution. And again, this has to do with the fact that the atoms at the surface the distance from those atoms at the surface to the ones below is shorter than the platinum-platinum distance in the middle of the particle. Let me go to Zane's now. So far so good for the EXAFS. Let's now go to the edge and let's see what we can do there in a spectroscopic way. So we call this X-ray absorption near X structure. And let's go to one example which we have done over the past years, which is aluminum 1s. If you kick out a 1s electron from an aluminium, then this costs you 1.6 kilo electron volt, and those who do XPS know that, because this is the aluminium anode. It also means that this is a low energy, and it means that this kind of an energy, this kind of an X-ray, is absorbed by air, strongly. And that means we cannot measure in air. We are in the soft X-ray region, so we must measure under vacuum. And this means that we are sort of under surface science conditions, not completely, but almost. And this makes the experiment somewhat more difficult. You can do it here. We learned yesterday they have stations for soft X-rays here. So for the Canadians, if you want to do things like that, you can do it here. Because we are very much interested not only in molybdenum sulfide, but also in zeolites, we have quite a program with NMR, high field NMR, magic angle spinning solid state, but also in EXAFS. Because in EXAFS, when you can do things easier at higher temperatures. So here are a lot of model compounds, here are the edges, and now you see a lot of structure. And we just use this in a spectroscopic fingerprinting type of a way. For instance, here you see zeolites, you see a peak here and a peak there, and these are all octahedral compounds and these are tetrahedral compounds. And you see there are differences. When I plot them over each other, you see that the octahedral has two peaks close to each other, and the tetrahedral has this broad one here and a peak more to the left. So if a peak comes up here, we know it's octahedral, and when we start tetrahedral, and things like that. So we use this in the fingerprinting way to see if our de-illumination of zeolites is successful. Did we remove it fully, or did we make it transform it into octahedral or whatever? And you can do studies like here. The octahedral by heat treatment can be brought back. So we have shown by this method that not all octahedral is extra framework. We have several publications, NMR and EXAFS, or Zane's, that show that quite a bit of the octahedral can be brought back to a tetrahedral position. So our opinion is that this octahedral aluminium is still hanging on the lattice. It just has taken up a few waters, and it has gone from tetrahedral to octahedral, but when you remove the water by heating, drying, then you go tetrahedral again. Of course, there is still also some octahedral, which is the so-called extra framework aluminium. But that's not the 100% story. So you can do the NMR, you can do similar things. For instance, here is an amorphous silica alumina. You can see also by ammonia you can do it. Even in the amorphous silica alumina, you have the octahedral peak at almost 0 ppm, this aluminium NMR, and the one at about 60 for the tetrahedral. And this normally would have been, you would have thought that that is the octahedral aluminium of the gamma alumina type, which you have in amorphous silica alumina. But you see, if you have only 14% aluminium content, most of your aluminium is really tetrahedral. Because even this can be brought to tetrahedral. You increase this, meaning that only very little bit is really octahedral. And under the wet conditions, well, it's just hanging on there. It was at tetrahedral, but it expands by taking up water, but it still belongs to the tetrahedral part. Of course, when you go up in the aluminium content, then you introduce too much aluminium. It cannot be taken up, apparently, in aluminium tetrahedral positions, in zeolitic type of positions, be it amorphous, in the silica. And yes, indeed, then the ammonia trick does bring it down, but not completely. And indeed, now it's a real octahedral. So these are gamma alumina domains, or eta alumina domains, if you will. And you can look at it with two-dimensional NMR. This is a spectrum which we measured with a 700 megahertz machine that we, together with a few colleagues, recently got. And then you do it in 2 dimensions, like you do in organic chemistry, and you can distinguish between tetrahedral, and also the so-called pentagonal peak can be analyzed, and you can try to find out if that belongs to really tetrahedral or really octahedral, or if it's really pentagonal. So these kinds of studies in combination with Zanes are very important. Let me give you one more example of Zanes, and that is gold. Gold, of course, has become a bandwagon in catalysis. Since people are working on fuel cells, you have to remove the last traces of CO. And one way of doing it, and Haruta discovered that, is take gold. You cannot oxidize the CO on gold, because gold absorbs the oxygen well and can split it. But gold has very great difficulty splitting the hydrogen. So if you have a mixture of a lot of hydrogen and a little bit of CO, it's the CO which can be oxidized to CO2 and then can be removed. Whereas you don't waste the hydrogen going to water. And so there is a lot of research now suddenly on gold. And if you go to the gold L3 edge, which means you kick out the 2p electron, and if you would go further, you would go to the EXAFS, but if we just look right at the edge, you see what is called a white line. Since the days of photographic paper, this is called white line, because on the photographic paper, it's the reverse color. So in this case, the strong intensity gives you white line. That's the name. And why is it there? If you have metallic gold, it has no white line. If you have an oxidic gold, it has it. And that's because what you do here, the 2p electron is promoted to the 5d level. And that's an allowed transition, p to d. But that means there must be holes, there must be an empty place for the electron to go to the 5d level. Now in gold, the 5d band is full. Whereas in the oxidic gold, the 3+, you have empty holes. So now the electron can go here, so you see intensity. That's the story. And you can see that the reduction of gold by hydrogen is easy. This was done at, 70 degrees up, temperature probe reduction, and then on the fly you measure the Zanes in this case. You see the isoplastic points, where you go from gold 3+ to gold 0. And there are many systems you can study. For instance, many metals do it. Also the 4D series, silver, palladium, and so on to molybdenum. The more you go to the left in the periodic table, here you see it, silver going to the left to molybdenum. In silver, the D band is full. In molybdenum, it's half full. So here, you can go from the 2p to, in this case, the 4D, and you have the highest chance of doing it, because here are more holes than here, and that's what you see. Silver has no white line, palladium has one, and molybdenum has the strongest, and here they are plural. You can also do alloy studies. You can alloy palladium with silver, and you can see that pure palladium has it, pure silver doesn't have it, and in between, it's in between. So you can also do that kind of thing. And then here is one of the latest results, and we are very proud of being able to show you. This is one of my coworkers, Dr. van Bokhoven, who is in my group since a few years. This is gold Zanes, and normally you would see what I showed you, the black line. This is what has been published over and over, and also by us and anybody, and without any white line. And the reason is that you don't see much is that the resolution isn't good enough. And we had always thought, why isn't there a little bit of a D hole? Because you have the D band and the S band, and when you have the hybridization, it's like a water reservoir, the empty holes in the S band, so you can pump electrons from the D band into the S band, so you free holes in the D band, so you must have some intensity there. And why was there nothing? The answer is there is something. Look at the red curve. There is. What is the red curve? It's the same foil, gold foil, but now measured with a different analyzer. What I've shown you until now is normal EXAFS. We have our sample, the X-rays go through, We have an ionization chamber behind the sample which measures the intensity of the X-rays. So you measure the absorption of the X-rays. So what you do is you kick out an electron from a deep level, it goes to infinite, and you leave a hole in a deep level. Now the deeper this level, the quicker it fills. So the lifetime of this hole determines the line width of your spectrum. This is Heisenberg uncertainty principle. So here we are talking about, as you see, 12 kiloelectron volts, 12,000 electron volts. That's quite deep. So the line width is 1, 2 electron volts. And that's why it smears out. If we smear the red one, we get the black one. But both are experimentally measured. The one with the classic. I said, now how did we do the red one? Oh, this is a nice trick. It has been known for years. But only since the new generation of synchrotrons can we do it. If we come up with the right detector. What did we do here? We didn't detect the X-rays behind our sample. We measured the fluorescent photons. What happens is that this hole here is being filled by electrons in higher orbitals. So an electron falls down and fills this hole. And you're left now with a hole here, up here. This is much more shallow. So this is just 1 or 2 kiloelectron volts. So the uncertainty principle tells you, Heisenberg, the old Mr. Heisenberg tells you, that now the lifetime is much longer. So the line width is much shorter. And that's what we see. So what we did, we took a fluorescent detector and we positioned it in line, and we also live of the high brilliance of the ring in Grenoble, right? We measured this in Grenoble. And then you see the red line. Now the problem is you can't do this daily, it also takes hours of measuring time, whereas the black one was done in a couple of minutes. But you see what will be the future. The future will be the fluorescent detection. And of course, and we knew it a long time, we couldn't do it. And we have now done it, and we are the first to publish this. And it's just been accepted. We'll go to Angewandte Chemie, look out for it, and you'll see what is the problem. And this is theory. On the right, it's theory, what EXAFS theory. This is a DFT type of a model predicts. So you see, it's in agreement. One more. This is oxygen. So this is the CO oxidation with the high resolution. And you can see that it goes down and so on. So our present model of the CO oxidation is that it is gold zero. Because there are two theories floating around, that it is the cationic gold doing it. This is Bruce Gates and his mafia. And then there is the other group, and there are many groups, but basically it's gold zero versus gold cationic. I think, well, it's not the final word yet, but I think we are on our way with this kind of measurement. With that, I want to finish. Let me skip that one and go directly to thank my co-workers, my students. Stefan Lauwers, a Dutch guy years ago who started to do EXAFS in my group, then Lorenzo Medici and Riccardo Cattaneo from the Italian part of Switzerland, Daniele Nicosia, a little bit more south from from Sicily, Evelyn Bush, who is from Holland, Takafumi Shido from Japan, Vivian Schwartz, originally from Brazil, but maybe she's American by now, Thomas Weber, he is German, and Jeroen van Bokhoven did those gold measurements I showed you lately. And he is Dutch originally, and he's in my group. Thank you very much for your attention.
We have time for a few questions. Can you just take the questions?
Yes.
What was the support for the gold cluster work? What was the support after gold clusters and CO oxidation work?
I think it was aluminum.
So it could be different on
Yes.
other supports.
Yes.
Series.
Yes. Yes, we are aware of that. Yeah. So we have to do more work. But as I said, with this high resolution, it takes a lot of time, and we don't, even in Grenoble, with this success, you don't get it daily. Sorry.
First, I want to make sure I understand. When you were talking about the molecular sulfide, you did the calculation on the external layer and then internal layer. for molybdenum bond distance, right?
Yeah.
That's for molysulfide.
Yeah.
That's a calculation that's not really the DFT type calculation.
What do you mean?
I'm sorry. I should have said that people were building the models looking at the different edge, different sulfur edge, and different molybdenum edge.
Yes.
So from your work on the molybdenum bond distance, can you elaborate a little more on what you learned and back into the model in the
No. This work was already done before the outburst of the DFT results.
Okay.
All I want to say with that modeling is that you can only explain away the discrepancy between the old EXAFS model and the TEM if you allow for distortion at the edge, and we can roughly say what the distortion is. But that's the best, as far as I can go.
Okay.
I cannot pin it down and try to use it to prove DFT or vice versa.
Okay.
Forget it. No. I will never say that.
All right. Okay. Yeah. Just to verify that. Thank you.
DFT is so holy, John.
Which gold OJ line did you look at for your gold work? Because it couldn't have been the K alpha, it had to be one more shallow OJ line, like the M beta or something like that.
Yeah.
Do you think that's going to be a concern then if you try to look at other things? If you look at a name per system, that's the only OJ line you're going to have in there. But if you start having other competing OJ lines in there, it's going to limit the usefulness of that.
Yeah. We have to look at that. Yeah. But the idea is old. In our field, it was there.
Yeah. No.
We just had to do it.
What is the time resolution for taking your EXAFS spectra? For example, looking at the changes of the nanoparticles of molysulfide. Can you study the transformation, agglomeration with a real time frame in your measurements?
Oh, can you give me one of the last slides? Go to the last part 5, something like that. Number 48. Yes, click it. Yeah. Okay. Now, okay, I jumped over this one because of time. I showed you quick EXAFS. Now, quick EXAFS is a sort of poor man's thing. You can go much faster than that because in the ring. For those of you who don't know anything about that, I'm sorry for those who know everything, but you'll hear later that there are pockets of electrons going around the ring, and when they go around the corner, bended away by a magnet, for instance, you get the singleton radiation, which is continuum from very hard X-rays to soft, whatever have you. Now, these bunches of electrons are certain distance apart, which is also time. So you can use that time frame of the singletron. You can measure, let's say, the light coming out of this pocket of electrons and out of the next, and so on. And that's very quick. Then you go to a nanosecond. And so in physics, people, and also in chemistry, physical chemistry first, you can use that kind of time domain. Now, at the Spring 8 ring, the people from Tokyo have looked at a rhodium catalyst, for instance, and they've done it. It's still kind of slow. As you see, they have done it with a resolution of, let's say, 10.1 of a second. It is here 2,000 milliseconds, but you see there are many spectra in between. So the distance between the spectra was a tenth of a second. And that is already quite fast, much faster than I showed you in our quick EXAFS. And so that is, and then you get similar spectra as I showed you, again quick EXAFS, but you can go even faster because you can go to the nanosecond domain. And so there are beautiful things to do there. If it makes sense in catalysis, I don't know, it's up to you. For instance, in this case, can I continue? Yeah. So here, for instance, is the outcome. Let me jump to the result. It's a system I did when I was still in Holland, well, that's a long time ago. And they did it now with time resolution. This is why it interests me much. When you have rhodium particles, small rhodium particles on alumina, because mainly on alumina you can make those very small, you absorb CO on it, the outcome is that you have single rhodium atoms with two COs on top of it. And for a long time this was a problem. How can this be? Actually it's a rhodium cation. What happens is, in the time frame, in less than a second, you get the adsorption. And then in another second, the atoms are being pushed aside. And the reason thermodynamically is, of course, that every rhodium atom prefers to have two instead of one. And therefore, you get this pushing power aside. And at the same time, the rhodium atom is meeting OH groups of the support, and the OH is oxidizing the rhodium. And you get hydrogen gas. John Yates has done this years ago. He has seen the hydrogen. And so in the end, we have called this corrosive chemisorption. And it's I think one of the nicest examples in the early days of EXAFS, that you can see these things. The beauty was that we had very small particles, and in the end you end with this. And now Iwasawa has done it on this time scale. And you can see all the single steps. And that's the kind of thing you may expect to see more and more of.
Thank you very much, Professor Prins. Okay, this is working. We're going to need 5 minutes to set up. We have to move things around a little bit before our industry panel. So 5 minutes only.